everyone. Can everyone hear me? Right? Do I need a mic or are you guys okay? Okay? Good. Thank you very, very much for coming to my talk. I've got a confession to make. I am not actually a developer, I'm a recruiter. Right, I'm kidding. I'm kidding. I'm kidding. My name's Sam. I've worked with, I've been coding for about 12 to 14 years, more or less. And traditionally, I was a .NET developer. Up till 2000, maybe 13, I was building websites, APIs, and then I sort of transitioned and moved into the big data space. And the reason being, I was asked to come and lead a team in my old place to bring in some engineering practices. And part of this talk is walking you through the issues that we face and the failures really that we had, because as engineers, that's how we learn, right? We're in a very unique industry where we learn from our failures. If you were a pilot and you kept crashing on takeoff, you wouldn't be a pilot for long, right? But with us, the motto was always fail fast. So that's what I'm hoping to achieve today, to show you what I've learned along the way and hopefully give you a few ideas. Out of interest here, who is interested in big data or thinking of a transition career? Okay, all right then, a few of you. So the question you ask yourself is like, why? You know, I was building APIs and websites. It was interesting, even though I had to learn a new JavaScript framework every other week. But it was still interesting, right? It were interesting problems. But I quickly started to realize that the unique selling point between company A and company B isn't their tech, isn't their underlying tech. It's how they use their data for customer behavior. So companies like WhatsApp and Instagram sold for billions, not because Facebook couldn't do a chat app or an image filter program. It's because of how well they understood their customers and how well they understood their data. And at the time, when I was doing APIs, I was like, there's a wealth of data here that we could use to understand our customers better. And that's why I was approached to lead that team. To give you an idea, people who are familiar with event sourcing, if you go to a website and you add 3 things to your basket, and then you add a 4th, but you're not quite sure, so you remove that 4th. That sort of interaction is really interesting for both marketeers and analysts. Why did you remove that 4th item? By the time people look at the analytics and it reaches the database, it looked like the user had only 3 items. So you missed that context, that little bit of information. So you sort of ask yourself, what is big data? And I sort of like this tweet because it's pretty old, but I'm not going to say it out loud. But no one has a strict definition of what big data is, right? Multiple people have tried to define it. But I think the most concise definition is from IBM, which is the 3 V's. The first one is volume, how much data you have, right? So how many here think, 100,000 records is big data? 1 million, 10 million, 100 million, 100 terabytes of data, is that big data? So to me, the definition is not on size, it's when the data has to be distributed within a cluster. If it can't be held within one single node, that's when you need distributed power, and that's when I could classify it as big data when it comes to size. The next V is velocity. How fast this data is coming through. Is it coming once a day? Is it coming once a minute, once an hour, once a microsecond? How fast it's going through your system. And the last V is variety. How many different data points do you have? Is it your main platform? Is it coming from Google? Is it coming from Facebook, Twitter? All these different data sources add a variety to your end data, and it gives you a bigger perspective of what your customers are actually doing. So the first term I had to learn is ETL, which is the bread and butter of the big data world. And this has been going on for years, way before big data actually became a thing, which is extracting your data, getting it from somewhere, transforming it or shaping it into the language of the business. So people might call something an order ref or a transaction ref, and it's order ID. It's very similar to the ubiquitous language of domain-driven design. It's just transforming it and shaping it in a way that your business understands, the language that you use within your meetings, really. And finally, the load into the data warehouse, which is copying it into so make it queryable. So this is how I came into the team. They had a Redshift data warehouse. Now, the difference between a data warehouse and a database is one is OLAP and one is OLTP. So online transactional processing versus online analytical processing. That basically means that, in layman terms, that it's been designed from the ground up for reading or designed from the ground up for writing. So your databases are talking to your e-commerce websites. These are transactional because there are more writes than reads. But for data warehouses, there's tens or hundreds of analysts looking at the same data. So they're geared up for reading. And that's why I came in and we had a Redshift data warehouse. We had a bunch of hard-coded Python scripts, ETL scripts that copy data from here, do a bit of transformation and load it. Everything, this is what I thought monoliths were bad, but that was a nightmare because in it was the management, the scheduling, some form of alerting being emails. In it was the transformations, in it was the backoffs. So it was a nightmare to work with. And not only was it hard-coded to a Windows box, and that Windows machine was up all the time. AWS would restart that box once a month for security upgrades. And at the time, we were like, oh, can you just not restart it? Because if it dies, we're screwed. But the NHS then happened, and we realized the security is really important. So the first thing we had to do was like, look, we need some form of immutable infrastructure, right? We need to run this code on Linux machines and spin them up as much as we want, because then we don't have a single point of failure. So that's what we did. We pushed it up to Team City at the time, and it will just have an agent running every 15 minutes. That gave us the ability to spin up as much machine as we want, and these are basic core engineering principles that you deal with when you're dealing with scale. The next problem was there was extremely slow updates. So the process took 8 or 9 hours to run. And the reason being is the BI team had no way of knowing what changed. So they went up and they got the last 30 or 40 days worth of data come back. And obviously that's over across 19 databases. That was a massive job. And it took 8 or 9 hours. And they had no ability to say, look, give us the deltas, give us what changed. So we went up to the engineering team and said, look, can you just give us a last updated column? So that way we can get the deltas. And they were like, no, because I'm not complaining about ORMs, but some ORMs are select star of everything. You add a new column, it breaks the whole system. And we tried it in a dev environment, and it just broke everything. So to fix that, what we did was we initially went to SQL Server, and they have something called change track control. And the idea is really simple. You point it to a table. Let's call this table X. And whenever a change is made in table X, it will then push the primary key of that table into an audit table with the timestamp of when it changed. So we're able to query this audit table to say, give us the last 15 minutes worth of data. And that's what we did. And then the failures became invisible. Like the BI team were like really happy. It was like, we haven't had a failure in months. Actually, the failures were still happening. It's just, it was a fail-fast system and it was invisible. Our SLA was, we'll make sure that you have the data from yesterday, not the last hour, for example. We quickly found a problem where Microsoft SQL Server would just clean up the audit table whenever they want. You have no control over when you want the cleanup to happen. That's a problem because when you have a very specific time of the day when you have a high number of orders coming in, and then suddenly Microsoft does, all right, we're going to do a cleanup, that your transactional database has a performance problem. And that's the database that is meant to do the orders. So we changed it into a trigger so we have more control over when the cleanup happens. So we reached a point where now we were getting new sources coming in. And you have to realize that initially all websites are one single website, a web server and database, and then they get split up for scale. And you have lots of little microservices, and each microservice has its own read model, it has their own database. So your job as a data engineer is to go into each and every one. And let's imagine this scenario where I'm an e-commerce website, and we realize that, you know what, if we assume if we implement social login, if we allow people to log in via Facebook, it lowers the barrier of entry for sign up, and hence people can order more. That everything we do in IT is assumptions. We assume A will give us B. We just use data to actually validate these assumptions. So what would happen is the people who are responsible, or the set of services that are responsible for authentication, will then implement this new feature, saying this user was a Facebook user, or this order was a Facebook order. But then BI won't be told about it till like a month later. So the business will then come say, OK, we've now had Facebook login for a month. How did we do? They don't go to the engineers, they go to the BI department, because that's where the owners of the data are. And then the BI team would be like, what? We've implemented Facebook login, we don't know about it. Let's go to the data engineering team and say, let's get that Facebook data orders, basically. And even if you're able to do it within a day or less than a day, you still have a month worth of data that you have to backfill, so you can tell how well we've done. So we realized that the hard-coded Python scripts were just not fit for purpose anymore. So we're like, OK, we've got to build a data pipeline. And we've actually got to use data technologies that will help us achieve this. So our end goal, or our primary goal of building this data pipeline, was we want everything queryable. Right? If there's any point of data somewhere there, we want the business to be able to query it wherever they are. And it has to be SQL-like, because that's what the analysts are comfortable with. It has to be, whatever we build on this pipeline, we have to be queryable via SQL-like language. So this is the architecture we went through. So we'd get raw files. The raw files could be CSV, JSON. I'll go into that in a minute. We push it into our data lake. So we separated the processing and the data science and the data serving layer, because there's a massive problem we face with Redshift and any traditional database or data warehouse, which is your storage, your data, is attached to your query engine. So the thing's actually running the queries. So the storage and the compute are attached together. And if you ever reach a point where you've got your ETL running all the time, you've got your data analysts calling dashboards off Tableau to say, look, this is how we've done yesterday or this week. And then you've got this other data scientist who decides to run a machine regression model across the history of your data. So that really affects the performance, and you can't go back saying, well, the dashboards are running slow because this particular data scientist is running entire history. So to do that, we've separated the storage and compute. So this Presto cluster would be your traditional analytics cluster. That's the thing serving dashboards. And this data science cluster would launch on demand. Whenever someone wants it, it will launch it. And then you look at the schemas of the files on S3 and look at what your table will look like. So we have no problem of the processing engine being too slow, because they're completely separate from where the data is actually stored. Data lake is literally a place of structured and unstructured data. So you can dump things like JSONs there, and you have to figure out how you're going to link it to your actual data. It's like a really, really big data warehouse, but at the same time, with a data warehouse, you have to define schemas and stuff. With a data lake, it's just S3. It is a dumping ground, but it very quickly becomes a swamp, because you realize I've got so much data here. How do I link it? How do I actually make sense of it? So our job as data engineers is to make sure it's queryable and it's understandable by the business. We also had to handle bad data, which is a really big pain, because you have no control over your data providers, right? So they can send you, let's say they send you a CSV file, and some of the columns on that file are meant to be integers or doubles or so on, and it has weird characters there, right? It has letters. Or things are timestamps, but they're not in UTC, they're in BST, or they're in the US time zone. Or they give you a date column, but it's formatted year, day, month, because it's come from the US provider. Those are really annoying things that you have to handle. So how we handled it is when we attach the schema to our code base. So every time we run a deploy, every time we run our ETL, it checks whether the file that arrived is the schema we expect. And what it is, then we can start processing the file. So the schemas are directly coupled to our code. We were able to handle schema updates, and that's in the Facebook example, and I'll go through that in the demo, where someone implements Facebook login. And this wasn't really a business problem, more about the engineers being lazy. We wanted it to be seamless. So if we call an API, which returns JSON, and this API now returns a new field, we didn't want to do any more work to implement that new field to make it queryable. It has to be seamless completely. That was a really big pain because traditionally when we're working with Redshift, let's say you've got a table with 30 or 40 terabytes of data, then there's a new column that comes in. It's nullable to the past, that's fine, but you can't amend it like you would in SQL Server. You would have to create a temp table with this new column, copy all that data from the old table onto this new table with the new column, and then get rid of the old table. It's just a pain, and that's why we wanted to handle schema updates more efficiently. We also added alerting to it. So every time that we have a failure in the 15-minute run, everyone's aware, it's visible. We added a dashboard so everyone can see what's happening, when we found out the problem, and when we actually fixed it. And that's really when we started seeing a lot of faith from the business to the data engineering team. Not when it became bulletproof, but because then now they're visible to say, OK, the reason I remember having a conversation with a data analyst and said that's when the light switched on. I realized we went and said there's a problem, and you said we are aware of the problem. This is how we are aware, and you see this dashboard that we sent you months ago. If you were looking at it, you'll know how we found out and exactly when we'll fix it. So yeah, alerting really helped. So the data formats that's bread and butter for when you're doing big data, you've got CSVs and JSONs, right? The problem with these things are it's very, very difficult to open a 20 gig file on your machine via text editor. So that's why formats like Parquet and Avro came in. And they're different because the data is stored columnary. And what that means is, actually, this will explain it much better. So say you've got your traditional table there, right? And you've got terabytes of data there. But this column here is an varchar, or varchar or a string. That's a string. That's a date. And that's a float, decimal. It's a value, right? The amount of compression you can do on this row, that's how they're stored traditionally via rows. That's how they're partitioned, is very, very small because there's so much discrepancies between the value. What columnar storage does is you're storing the entire column together. So you know all the data types in that column are going to be the same. So the amount of compression you can do is much higher, and hence the data becomes smaller and more manageable. So that's what we did. We worked with Parquet. So this is a more in-depth look of what our data lake looks like. So we get raw files from via CSV or JSON from either an API or a CSV dump or an S3 sync. And then what we do is we then read it into Spark, and we convert it to Parquet. But the file remains the same. It's just more manageable now. So we save that back into back into S3. And then we read that file again, and we model it. So that's the transform part. We model it into the shape of the business, and we save that back to S3. So this last step here is not required. However, we wanted to do it for separating of the storage and the compute. What we do with the model data in this last step is then we do all the joins to mirror the end table that is going to be used by analysts. And then we save that back to S3. So then we can use things like Presto to say, look, this is where the data warehouse table is. This is what the schema is like. And now you can allow people to query it. That allows us to separate the storage and compute. However, if you're just going to push things to Redshift, you can do the joins after that and just push it directly. You don't have to model it back. However, AWS do tell you to do it this way. If you want to do things like use AWS Athena and Spectrum, I think Redshift Spectrum, which basically means you're right on Redshift and you write a query to S3. So we use Spark for our engine. And there's two main important things that Spark gives us. One is invisible to the business, and one is very highly visible. The invisible part is the fact that it's a distributed cluster. So it distributes the data throughout the cluster. And if any of the nodes fail or lose the data, there are copies throughout the cluster that can recover. We recover from failure. It's completely invisible to us. And neither the data engineers or the analysts or the scientists have to worry about this data. The visible thing is it works with 4 or 5 different languages within the same engine. So people who are comfortable with Scala and Java, and then there's Python, there's SQL, there's R for people who like R for some reason. So you can work with that same language, and you work with the same data, and you can then share notebooks, share your code, basically. And that's really powerful because then it's all within the same engine and it's consistent, basically. You can share APIs. We also added a DAG. So what a DAG is a direct acyclic graph. And that's basically a really fancy way of saying a dependency tree. So remember table X I was talking about earlier? Let's say this table X is dependent on 5 different tables. It's a join of 5 different tables. Traditionally, what we were doing in that hard-coded Python scripts was, like, we need to build all these 5 tables and then build that. But to make it faster, we're going to do it async. We're not going to wait till all of them succeed. So 3 or 4 of them succeed. We try to build that table. It fails. The whole thing fails. With DAGs, and we use Airflow, Apache Airflow for that, it allows you to schedule things and say, look, with this thing depends on these things. So make sure these things finish before you try and build that. And it has things like retries. Retry it for 5 or 6 times if you want. Back off for an hour between retries. Alert to SNS, SQS, and PagerDuty. It's just a very, very nice framework that allows us to do this in a very easy way. It's been designed for scheduling. And that just makes our code a lot simpler. All we have to do is focus on the transformations. And that's all our code base is. I've got a blog post detailing each and every step of building a data pipeline. And there's a section on Airflow to get you started. So have a look at that if you're interested in building a data pipeline. So, but that's not the last step. We've imported the data, we're modeling it correctly, but we still need a data serving layer because we need people to query it via SQL, right? That was our underlying goal. And that's when Presto comes in. We basically tell Presto, this is where the data is, and this is the shape of the data, and just accept SQL queries against it. We initially went with Presto because we were looking at AWS Athena. It wasn't available in Europe early this year. It became available, but we had a lot of issues with AWS Athena because the Hive connector is not quite up to date. So things like our schemas had to be lowercase for some weird reason. The version of Hive on Athena was supposedly able to use it, but it says in the documentation we just can't do it. It can't handle things like date columns, which is really annoying. So they were like, OK, convert all your dates to timestamps. And we're like, you know what, we'll just hold off. It's working now. We'll wait till you fix all these bugs before we transition. But the fact is Presto and Athena are exactly the same, so you can easily transition between the two. You don't have to copy any data. You just say, look, here's a schema, and this is where the data is. So we also implemented a Lambda architecture. And what Lambda architecture is splitting the fast versus the slow. So slow data is the thing that gets dropped once a day. The fast data is things like Twitter streams, right? You don't want to see things like what's trending on Twitter 6 months ago, unless if you want to, but most people would be like, show me what's trending now. So what we want to do is like, OK, we'll launch a Kafka cluster to make sure we have the stream layer, and we'll get data from Kafka. And this is basically what streaming is. Everything comes in a second, a big JSON blob, and you save it to your data lake to make it queryable. The problem we faced is we went to, there's no managed Kafka service, right? So we go to our CTO and we said, look, we're going to need 100 grand for a quarter because we need to hire X amount of engineers to build this Kafka cluster. Not only that, but we also need to ensure all the business pushes data into Kafka. They're producers of the data, so we can consume it, and everyone else in the business can. That was a massive heartache. And that's basically when he said, no, find a cheaper way of proving this value. And that's when we went to Kinesis streams, and you're able to say to Kinesis, look, here's a topic, here's a stream, and then we, as a consumer of that data, we have to know where we were in the stream and basically say, OK, give me the latest data. Say there were 10 streams, we read up to number 2, we go quiet for a bit and say, OK, the last thing we read was the second record, give me everything. It's called an offset, give me the rest of the offset. And then once you read it, that's where your current offset is. That's kind of a problem with streaming. That's where the Spark people came up with continuous applications, and which is people don't just do streaming. They always do something with the streaming data, whether it's saving it to a sink, whether it's running live queries on it. So when you're asking a question like what's trending, and they wanted to really unify the batch and the streaming model together to make it simpler for engineers and for analysts and for scientists. And that's where structured streaming came in. And it allows you to define a checkpoint directory, and I'll show you that in the demo. But basically it says, here's my checkpoint directory, and I'm going to start reading a stream. If it dies for any particular reason, I can just start again and continue where I left off. And it's really, really simple. And you don't have to do all the code that you have to do with Kafka, for example. And then we came into BigQuery. So all that time, we were still doing Redshift. And then we realized that amending schemas in Redshift is really annoying. They're copying from temp tables. And what the certain members of the BI team were doing is they had Google Analytics. And Google Analytics, what our responsibilities as data engineers was to get the data from Google and push it into Redshift. And Redshift was tremendously slow because, one, it's columnar storage again. And what it's meant to, you only query the columns you need. The more columns you query, because they're distributed that way, the more data you're getting back, and hence it's slower. And all analysts, without failure, whenever they get, even myself really, whenever I come to a new database, the first thing I do is select star. And that's really bad. So we had two options there. One, try and educate analysts to say, look, you have to choose the right queries. But also, you've got to design your tables from the start really well using sort keys and disk keys. And these are partition keys, really, and how the data is distributed. Or we can move to something like BigQuery, which they were doing. They were writing the most awful queries you want. And what BigQuery does is you're not paying for that cluster being up and running. It pushes whatever horrible query you write to hundreds of thousands of Google machines and returns that data within seconds. The caveat there is you are paying for your bad queries. You're paying for that abstraction, right? But the thing is, you can then query 35 terabytes of data for like $30 or something, right? So if your entire data warehouse is 10 or 20 or 40 terabytes, very easy to come up and you spend less than $100 to just say, look, let's do a proof of concept. And you write as many bad queries as you want, it's fine. But the point is you can set limits and stuff, but you'll never pay more than £500 for, regardless of how crappy your data is, because it does some sort of caching. So you write a bad query, someone else writes an equally bad query, but you're returning the same things, it's cached. It's very easy to get it. But the reason we wanted to go with it as data engineers is it allows us to amend schemas as much as we want. And a new field comes in, that is Facebook login comes in. We push the BigQuery and then say, look, this is now a new column. It amends it. It does all the shifting of the temp table invisible, and you don't see it. I'll show that in the demo. Realize that there's no way of copying Parquet data into BigQuery. So as an engineer would do, I just wrote one. And there isn't one at the time. So this connector allows us to basically copy stuff, uses Spark, do our transformations, copy it to BigQuery, and then do the schema updates. So feel free to check it out and give me some feedback if you can. So that's when that's when we realized, OK, now we're listening to these Kinesis streams. Let's do some machine learning on it. So and Spark comes with an MLlib package. And so imagine on the weekend, I like to, I'm a woman during the weekend. So I'm Samantha on the weekend, and I'm shopping at this e-commerce website for clothes, and I've bought 9 products. But then another relatively the same age woman has bought 10 items, right? But my 9 items are the same as her 9 items, so we have similar tastes. So we can use a matrix to say, look, these people have the same taste, so we show them recommendations based on their tastes. It's very, very similar to Amazon's people who bought this also bought that, but it's just more personalized to your taste. And that's what we did with the MLlib package. It's called least alternating squares, or ALM, I think, the ALM metrics. But basically, it's a big matrix of saying this likes that, and this person likes this, and it's very, very simple to do. So now I'm going to show you the demo, but to do the demo, I might need to mirror. Right, so imagine what I've done here on this massively over-provisioned Mac is I've created a data lake, right? And this data lake has, assuming we call an API, and this API returns this JSON. This is not very readable, so what I've done is I've just gone into JSON lint and showed you what the JSON looks like. So it's a nested JSON. Redshift had a very big issue with having nested, so that's kind of why we moved to BigQuery. With Redshift, we had to explode and make, by explode, it's very, very rude to say explode nowadays for other reasons, but what explode means is you take an array of things and you basically expand it to look at the entire row, but to deal with nested structures, because all JSON's nested when you're returning APIs. So let's say this one is user agent. So user agent is maybe 3 levels down or 2 levels down? Yeah, no, 3 levels down. And the API returns that. So what I've done is I have a data lake folder. And this can be anywhere. It could be in S3, it could be Google Cloud Storage, wherever you want. And you can point Spark to it. So I'll show you the code. It's really, really simple. It's all on GitHub, but I'll wait while it loads up. Luckily, IntelliJ is slightly faster than Visual Studio, so you may or may not be waiting too long. So let's open that, and I'll show you the code, hopefully, if I can zoom in. Scanning, it's the indexing that's annoying. So this is the code. Let's see if I can zoom in. So that's the start of the main function there. Let's add line numbers to help explain. There. So line 31 is the start of the main function. What I'm doing is setting up logging. All this is just setup. You do that at the very start. In most clusters, I think you don't even need to do that. So I've created a table called build stuff demo. And I'm saying read all the JSON from data lake. And that's my data lake. And notice that I haven't even told it what the schema is, right? It will automatically pick the schema infer the schema from the JSON. And then I'm just saying, keep the query running all the time, and basically wait till you die. So then I copy this JSON file into the data lake, and I kick off. So if I go to terminal and I basically start the application, what will happen is it will spin up the daemon, and it will say, look, I'm going to start looking at a particular data lake. Over there, can I not zoom in here? No, I can. So where are we looking at where it found the schema? So there it's adding that file. So it saw the file. There is when it figured out, inferred the schema from it. If you go to, it says it created table build stuff demo. So if you go into BigQuery, see there's nothing in test. However, if I refresh the page, hopefully without internet failure, I should see the table there, build stuff demo, and then that's our JSON, right? That's exactly our JSON. And if I say I want to query, what was it, user agent? So there you go. Run that query, and that's just normal SQL, and boom, that is your JSON. So what happens if then the APIs now return the social login? So I've got this is Facebook login. So now the API is returning a Boolean value to say this particular order blob is a Facebook order. All I have to do is kill that and then copy the new orders to my massive data lake, and then start the streaming lesson again. Streaming job again. And then what we'll do is you'll notice here that this is all part of the connector, but it also comes free with Spark. You point it to a checkpoint directory, so it knows where it's looking at. And this transaction log is what I've written to basically say, ensure I don't write anything twice. So what it's happening is it says, OK, in the data lake folder here, I've already seen orders, so I'm not going to do it again. And I'm going to pick up orders too. Now, if you look at the schema on this one, you will see that there's no is Facebook login. Right? It normally adds it at the bottom, but it's not there, and there's only one record there, which is the original orders. And if we wait for a bit, and then it's finished, So if I now refresh the page with the schema, we have got is Facebook login there. So if I query this table again, and I want to query our new field, there, the first one's null, it's true. That took us at least 3 or 4 hours when it was back in Redshift world. But then you sort of ask yourself, and you're like, Sam, you're returning 1 byte. That's not exactly a big data, right? So what I wanted to do was I wanted to query all of GitHub. Like it's all the entirety of GitHub. And if we open that, so what I'm going to fire query is give me the commit, the messages, repo name from the entirety of GitHub, but where the author is me, right? So Sam Elamin, right. So it's running now. I have yet to run a query on BigQuery, regardless of the size of the data that returns within more than 20 odd seconds. So there you go. That's okay. Let's format that query. Let's try and zoom in as well so you can see what's happening. Is that clear? Yeah. So we're limiting by the author, and the results are there. You can download them as well. But let me just zoom out so I can show you what. So these are some commits to the Apache Spark project, for example. But to make it more interesting, give me a name of what the most popular, give me a name of a repo, basically. A GitHub repo, any repo. Redshift? REST-sharp. OK, so let's have a look at where REST-sharp is on GitHub. There you go. Yeah, the internet's really bad. I shouldn't have done these dynamic demos. Right, so, and then I go into my query history, and what I want to do is, yeah, so let's go and open that. So what I want is I want to query REST-sharp and give me the committers, basically, for REST-sharp. And now you can't really see it here, can you? No, you can. It just did 134 gigs in 3 seconds. So what if I want to see, what if I want something more interesting and say, look, I want to find out, who has been contributing to REST-sharp the most. So we do group by, is it author.name? And then order by count star sending. Let's see. Let's hope this works. I've actually never done this. So I'm hoping to find out who is committing to REST-sharp the most. Actually, I'll need the author name as well, right? Otherwise, it doesn't make sense. So yeah, that just handled X amount of gigabytes of data, and now it's running again to get the author name. There, so Mr. John Sheehan is our lucky winner, and he's committed 232 to REST-sharp. So that's basically it. That was my journey into big data. And do you have any questions? Please feel free. If you don't, thank you very, very much for coming, and I hope I didn't disappoint.
How many dollars that query took you?
Less than $1, because it's 35 terabytes, and that's just 100 gigs. So
35 terabytes.
yeah, for like $30 or something. So I use it for, and actually, if I do, I'm not quite sure I will be charged for this because it's cached from our original count star, because it's still got the data, because it's a count star. But yeah, it's really powerful, basically, especially for exploration.
Is it cheaper go for the Google BigQuery?
I don't work for Google, so I can't answer that. However, for proof of concepts, to give you numbers, we were paying $20,000 a month for Redshift. We paid 100 there, just to get all our data and getting only 2 or 3 analysts to see if their performance would be better. By performance, I mean they didn't want to handle writing nice queries. They wanted to write ugly queries. So it was cheaper, but at the same time, we didn't have all our analysts dealing with it.
What about security perspective for you?
It's the same. The data stored in Google Cloud Storage, so it's the same security as Amazon S3, basically.
Is it secure or not?
Yeah, it is. It is. You have to define. You have to give people access via their emails. It's like IAM control. So it is secure. You can't go there and query it, basically, unless you mark the data as a public data. Like GitHub, yeah. Any?
My question, do you really need to do ETL, or you can do it sort of event-based, so you can real-time set updates to your data web?
That may work, but you still need to, that's basically what Kafka does. However, you're still trying to combine your batch data to your streaming data. Okay. And unifying that model is very difficult because your batch data is not going into Kafka. You can, but it's just a lot more work.
Does Google allow to run on-site?
No way. Yeah, you're paying for the Dremel engine down there, so you're not hosting it. So if you work in a bank which requires you to have the data on site, it might be difficult. Any further questions? Thank you very much. Have a very nice day and enjoy your conference.